Hi, welcome to Researcher's Help. So here we have studied about PID controller. So here mainly we have mentioned PID Vs Fractional Order PID controller. So in fractional order PID controller we have used FOMCON Toolbox in MATLAB. Okay, let's move on PID. So already you know the PID is the standard controller for all process. So it's a closed loop control system. So the closed loop control system having a set point and feedback. Set point minus feedback, it's produce error. So errors goes to controller. That controller output goes to process or plant. So from that we get the output. Normally in output side we have using a sensors. In before the process side we have using a final control element. Maybe it's a actuator or any of the depend upon the process. Okay, so PID controller already we know the linear term. So PID Kp into E of t is a proportional term, otherwise integral term and derivative terms. When it's convert into Laplace transform or S domain, it's convert into Kp plus Ka by S plus Kd into S. So this S terms here is a integer value, that means S power 1. So no floating values. So when you move on this fractional order PID controller, nothing but everything is same. So only difference is S power lambda and S power mu. This lambda and mu is the fractional order values. That means the values in between 0 to 1. So that's the difference in fractional order PID controller. Okay. PID versus PID. So already we know PID having a 3 parameters, happy K, KD, and a fractional order PID controller having additionally 2 parameters, lambda and mu. That value is between 0 to 1. So in PID easy to configure because only 3 variables. Already we know the Ziegler-Nicholas method or Bode plot method. So many methods we need to easy to tune the PID controller. But in fractional order PID controller we having a more than 2 values, so we need to concentrate to design. Already we know the PID controller easy to design in op-amp section also. That means unlock domain also we have easy to design. I think most of the process we are using a PID controller only. But FPID is having 2 additional parameters, so it's also get more efficient control. But it is compared to PID is complex to design. Okay, let's move on code. So before code, so what's the main problem? PID and FPID, the tuning is the main process. Without tuning, its performance is very poor. So the tuning, we need to achieve better or best KPK, that means controller parameters. So we have when move on code MATLAB code. Before that we know how we'll produce the random number generation with low and high values in MATLAB. It's similar to other language also. So in output equal to low plus high minus high value minus low value in the rand of 1. So it's produced the random value in between low and high value. Okay, we have move on code. Okay, so first of all, so in MATLAB we have derivative transfer function means already we know TF of. So we have first assigned the S parameter. Then we have derive like our plan model. So here using a plan model G. So I have taken the example of this function. We have identify the Bode plot means Bode of G. So it's produced. Already you know the x-axis is frequency and y-axis is phase and magnitude. From this Bode diagram also we have calibrate the Kp, Kd values. So it's like your Ziegler-Nicholas method. In the same way, we identify the stability also using Nyquist plot. So it's nothing but Nyquist plot. So here is a plus sign, they indicate the poles and zeros values. So when you identify the poles and zeros values means just under poles and G. So poles, sorry, I think it's don't have 0 values. Okay, this is a basic thing. Then we are move on our FPID code. So before this optimization, here I have mentioned this ID equal to 2 or 1. So 1 means PID and 2 means FPID. Okay, so here we have derive like how will derive our control system. So first of all, I have taken the PID controller. So I have taken the example how will produce the closed loop control system, because the G is the planned only. We don't derive any control system. So first of all, we have assigned KPKIDs. Now we have assigned normally 1. So produce the controller parameter. So it's produced the C value like this. So Kp already we have mentioned Kp plus Ka1 by S, Kd, yes. Okay, so when we have using a closed loop control system, so it's a procedure. So it's only for scripting, it's not a Simulink model, only scripting. So already we know the closed loop negative feedback control system. That means normal standard control system, C into G, comma 1. So it's produced a closed loop transfer function like T. So it's a overall our transfer function. So now we will give the input. So we have assigned the T value nothing but 0 is to 0.1 is to like anything. So if you assign that, then we have identify the step T comma T. So it's a step response of our plant. So here KP KD equal to 1, it's produce the step response output. So if you want like settling time, rising time, what are the parameters we need to means, you just enter step info. So already I have written here. It's produced rise time, settling minimum value. So each and every step parameters. Okay, let's move on our tuned procedures. So here I have written the code, nothing but simple code only. So in optimization we have using a random search optimization only. In iteration we have assigned like 50 iteration. So if you like want to more iteration means it's not a problem. So already I think I have mentioned lower bound and upper bound values. So from that we will get a optimal output. So first section is, so we run on our PID controller. So I assign ID equal to 1. So when run this code, it's produce so already we have is 100 iterations. The second subplot shows that so this is a KD value. This is the optimal value of KP. This is the PID controller, PID method. So x-axis derive the time consumption and y-axis is the amplitude of signal. So here is the fitness function. The blue color indicate the current iteration fitness value. So what's the fitness value here means we have using a integral square error. So integral square error we have taken as a fitness function. So red value indicates the optimal value. Optimal value means we have to identify the minimum ISC. So this is our one section. So if you move on other section, we are just assign 2, then run the code. So it's a fractional order PID controller. It's having more parameters like KP, KD and lambda and mu. So after 100 iteration, it gave the output like this. So here is the optimal parameter of lambda, mu and KP, KD. Okay, so if you want like your planned function is something different, like we have assigned the symbol order system means you just assign, then run the code. So you see the difference of response. So when you use so many persons use FPID, they have just confused how will handle this FPID and PID. So only I have created a common code so to do understand with between two things. Okay, this is our basic code. This is a random search optimization. I think already I have explained in previous videos. So here fitness function, how will calculate the error? The error will be calculated simple method only. Sum of absolute square error. That means integral absolute square error. Otherwise simply integral square error. So we on to the step info for is the rising time, settling time, each and every parameters. So this final value indicate the integral square. Thank you for watching. If any doubt, suggestion, kindly inform in comments. Okay, thank you so much.